Hello and welcome to Unit 4, Math of Chem, Lecture B. Today we're going to talk about moles and doing conversions and then briefly talk about something that we call hydrates. Okay, so moles are a unit of measure in chemistry, really super important. It lets us measure out elements and compounds in a lab situation where you can't actually count the number of little pieces. So they made a mole equivalent to whatever the gram formula mass of an element or a compound from the periodic table was, their relative masses. They compared them all to carbon-12 now. And then they did some math backwards to figure out how many pieces that would be. And the three significant figures, that's 6.02 times 10 to the 23rd units. So if we have this relationship, 1 mole is 6.02 times 10 to the 23rd units. If we do our factor label method, that means that we can have 6.02 times 10 to the 23rd units, whether it's atoms or molecules or pieces or timbits, per mole. Or you can write every 1 mole is 6.02 times 10 to the 23rd. It would be no different than using 1 dozen is 12 pieces, or that there are 12 pieces in every 1 dozen. It's the same kind of conversions, okay? But we're going to put chemical compounds to it, and 6.02 times 10 to the 23rd is a pretty big number, so it makes things a little more complicated. But if we just use our factor label method, and they want to know how many sodium atoms are in a sample containing 2 moles of sodium. You have 2 moles, and they want to know atoms. So when you pick your factor, you want to pick the factor where moles are on the bottom so that the moles cancel. And you put the 6.02 times 10 to the 23rd atoms at the top. So I wrote units here, but this could be atoms, it could be molecules, it could be whatever. The moles are going to cancel. And then if we look at our scientific calculator, 2 times 6.02. Now when you look at a scientific calculator, again, you're looking for either an EE or an EXP button. The one on your computer has EXP. And then we put in the exponent, 23. We don't have to hit the multiplication sign. We don't have to have any XY buttons, no parentheses. And it does the work for us. Now look, it put it in regular notation for us. It's going to be 1.2 times 10 to the 24th. So a pretty big amount of numbers. All right, if they give you molecules and they want you to convert in the opposite direction, so they're giving us 1.5 times 10 to the 23rd molecules, and they want to know how many moles we have. We're going to start by writing down what we have, 1.5 times 10 to the 23rd molecules. Notice that molecules and moles are not the same thing. This time I'm going to pick where the 1 mole is at the top. And I know in my factor I wrote units, but again, units could be anything, atoms or molecules or pieces. So we'll change that units to molecules, and the molecules will cancel. And I have 1.5 times 10 to the 23rd divided by 1.5 exp 23 divided by 6.02 to the 23rd. And I have 0.2 moles. There's a shortcut kind of way to memorize. I like to use the factor label, but we have this kind of mole triangle where we can go from one part to the next, always converting from moles. Whenever you're moving in, you're dividing by whatever the conversion factor is. Whenever you're moving out, you're multiplying by the conversion factor. So what this triangle tells me is if they give me numbers, if I need to change from numbers to moles, I'm going to divide by 6.02 times 10 to the 23rd. If they give me moles and I'm moving out towards numbers, I'm going to multiply by 6.02 times 10 to the 23rd. Okay? All right, let's move on to liters. When we look at liters, the relationship between moles and liters is that for every 1 liter or 1 mole, for every 1 mole of a gas at STP, so 1 mole, it's 22.4 liters. So again, we have our two conversion factors, 22.4 liters per every 1 mole or 1 mole per every 22.4 liters. If I'm going to set this up with factor label and they're giving me 0.25 moles and they want to know what volume that gas is, whenever they're talking about volume of a gas, they're talking about liters. So I'm going to do 0.25 moles times, and using our factor label, we want the moles to cancel, so we're going to pick the factor where the 1 mole is on the bottom and our 22.4 liters are on the top. So moles cancel, and we have, we closed the calculator, so we got to pull this guy back up. 0.25 times 22.4, or 5.6 liters. If we have the opposite, and they have a sample of gas at STP with a volume of 448 liters, and they want to know how many moles are in there, they gave us 448 liters. So when I use my factor label method, this time I want to pick the factor where the liters are on the bottom, 22.4 liters in every 1 mole, so that the liters cancel. And I have 448 divided by 22.4. And we have 20 liters. So pretty straightforward. It's just like the factor label we did at the beginning of the year. There's nothing tricky to it other than you have to memorize this relationship. These two relationships are not on your reference table anywhere. So you might want to, on your reference table somewhere, make a reminder to yourself that 1 mole is going to be equal to 6.02 times 10 to the 23rd, and I like to just use the term units, or it's 22.4 liters of a gas at STP, or the last one down there when we're talking about masses is going to be the gram formula mass, and we'll talk about what gram formula mass is in just a second. If we look at our triangle for mole conversions, here's volume of a gas at STP. If you give you liters and you want moles, then you divide by 22.4 liters. So moving in, we're dividing. If they give you moles and they want liters, you're going to multiply by 22.4 as you move out of our mole triangle. When it comes to numbers of pieces, this conversion factor is always the same, 6.02 times 10 to the 23rd. You're either going to divide moving in or multiply moving out. When we're talking about liters of a gas, the conversion factor is always the same. It's 22.4 liters. Divide going in, multiply going out. When we talk about mass, this is going to be different value depending on what element or compound we're talking about. We're always going to use the same factor. It's called the gram formula mass. And I tend to abbreviate that GFM, gram formula mass. It's going to be the sum of all of the atomic masses of either your element or your compound. So we'll still divide by the gram formula mass if you have a mass and you're trying to find moles. And we'll multiply by the gram formula mass if you're given moles and you're trying to figure out how many grams those are. But the number itself will not always be the same, and that's what makes it slightly tricky. All right, so if we look at gram formula mass, we are going to add up the atomic masses. So on your periodic table, in the upper left-hand square, there is a weighted average That's the atomic mass. I want you to round it to a whole number. If we happen to have an element and you look up sodium's gram formula mass is 23. And the units that they use here are sometimes called AMUs, or atomic mass units. Sometimes they just might call the unit U. I think that's the abbreviation that the state is using on your reference table now. And sometimes they will use the units grams per mole, because they set a mole as the amount that will be equal to the amount of the atomic mass in grams. So if I have 1 mole of sodium, it has a mass of 23 grams, or 23 grams per mole of sodium. That lets us use their atomic masses as our conversion factors when we do our factor label conversions. If we look at fluorine now instead of sodium, you have to be really careful because fluorine is diatomic. So if they just want to know what is the gram atomic mass of the element fluorine, and notice there's no subscript here, you're going to go to the periodic table, you're going to find fluorine square, you're going to look at his gram atomic mass, so that's 18.9964, and then you're going to round it to a whole number. So that's going to round to 19. And the gram atomic mass of fluorine is 19 grams per mole. That's for the element fluorine. But if they ask you for the gram atomic mass of fluorine gas, we have to remember that fluorine is diatomic. So if they want the gas itself, the formula isn't just F, it's F2. So that means I have 2 atoms of fluorine, and each one has a mass of 19. That's going to give us a total formula mass of 38 grams per mole. So you have to be slightly careful of the wording and make sure you watch for the diatomic ones. Okay, so an example of how we would solve a problem using gram formula mass to do a mole conversion. If I have a sample of helium that weighs 20 grams, and they want to know how many moles of helium that is, the first thing I'm going to do is find helium on my periodic table and find his mass. So helium's up here, and we have an atomic mass of 4. Helium is just 1 unit, so the atomic mass is 4 grams per mole. And then we just do factor label to convert. So we have 20 grams. We're going to put the 4 grams on the bottom because we want the grams to cancel. And we're going to put the 1 mole at the top because that's what we're trying to solve for. 20 divided by 4 is 5 moles. If you want to memorize this triangle, then this 4 grams per mole is the number you would use in here for the molar mass. So for helium, that would be 1 mole is 4 grams per mole. So they're calling it molar mass on this chart. Same math, I prefer to use the factor label method. You have another choice. If you go to reference table T, there is a box that says mole calculations right here. So if we were talking about helium, that exact same example, so they wanted to know how many moles of helium there are in 20 grams. Using that example in this equation, the number of moles was what they were asking for. That would be your X. The given mass was the 20 grams that they told you. And then down here, gram formula mass was the 4 grams per mole. And when you solve for X, we still get 5 moles. So I don't care which method you use. Either works for me. I just like the factor label because I don't have to memorize an equation or use any of the ones on the back. I just do the same math that we've been doing since September. Okay, if they give you moles, so they're saying if we have 0.5 moles of silver, how much does it weigh? So if they want to know how much it weighs, what they're really looking for are grams, and it's silver, so we're going to have to look up its gram formula mass. So we need a periodic table. Silver is Ag. If you don't have the symbol memorized, then make sure you check on table S. You don't want to get something wrong because you guessed at the element symbol. We round that off, so 107.99 is going to round off to 108. So the atomic mass here is 108, and remember it's grams per mole. So if I have 0.5 moles, this time when I set it up, I'm going to put the 1 mole on the bottom so that it cancels, and the 108 grams at the top. Moles cancel, and 0.5 times 108 is 54 grams. The next step then, after you can convert elements, is to just go on and do the exact same thing, but this time using compounds instead of elements. So the gram formula mass, or the gram molecular mass, so the mass of molecules, is going to be the exact same thing. So GFM, gram formula mass, and this time we're going to add up all of the pieces. So if we have sodium fluoride, there's 1 piece of sodium, and there is 1 piece of fluorine. We get those numbers from the subscripts. Remember, there's a 1 here. We just don't write it in. We already looked up the mass of 1 sodium. That was 23. And we looked up the mass of 1 fluorine. That was 19. And we add the 2 together. So carry the 1, and we have 42, and the units are grams per mole. And it's as simple as that. They can make this slightly harder by having you convert a name into a proper formula first. So chromium is Cr, and this 3, remember, goes with the chromium, and it tells me the charge. So the chromium has a charge of +3. Carbonate is a polyatomic ion, CO3, and it has a charge of -2. So to get this to balance and make a proper formula, I need the least common multiple between 3 and 2, which is 6. So my formula is going to be Cr2 parentheses CO3 and parentheses 3. So that's our proper formula. When we add up the gram formula mass then, and we count the pieces, we have to, and I'm going to do this way over here so there's room, we have to say there's 2 chromiums, there are 3 carbons, and there are 9 oxygens. And then I look up the masses. So chromium over here at 51.9 is going to round to 52. Carbon is 12, and oxygen at 15.9 is going to round to 16. So 52 and 12 and 16. So 2 times 52 is not bad, that's just 104, and 3 times 12 is just 36. But your multiples of 16 you might not be brushed up on yet. So 9 times 16 is 144. And then we add all of those up. So 4 and 6 is 10, and 4 more is 14. Carry the 1, 8, 284 grams per mole. Now notice if they just want the formula mass, if you can't turn the name into a proper formula in the first place, you're never going to get the correct formula mass. So you really have to have your naming skills down. If you're still having issues with naming, make sure you see me. We did talk a little bit about this common naming system when we have 2 nonmetals together, and you're supposed to know the prefixes. So dinitrogen means that I have 2 nitrogens. Pentoxide means that I have 5 oxygens. So when you add up the formula mass for this one, 2 nitrogens, 5 oxygens. Oxygen we already know is 16. And then nitrogen right here, 14. Two nitrogens at 14 each is 28. And 5 oxygens at 16 each is 80. And then we add the 2 together, and we have 108 grams per mole. All right, now when we're going to use that to do conversions, it's a little confusing at first because we have a sample of aluminum phosphate weighs 35 0.5 grams. How many moles does it contain? And it's not always obvious right away that you need the gram formula mass. But whenever they give you a mass in grams and they want moles, you will need the gram formula mass. So 1 aluminum, 1 phosphorus, and 4 oxygens. We already know the oxygens are 16 apiece. So 64. We need to look up aluminum and phosphorus. So again, we need our periodic table. Aluminum is right here, 26.9, so 27. And phosphorus is over here at 30.97, so 31. So 27 and 31. And I know I'm going quickly through that because I know where they are on the table, and you might not have caught up that fast. You can always pause it to look at those numbers to make sure you know where I got them from. 7 and 1 is 8, and 4 more is 12. Carry the 1. 6 and 3 is 9, and 1 is 10, and 2 is 12. So 122 grams per mole. Now you have a choice. You can do this the factor label way, which is the way that I prefer to do it. 30.5 grams times every 1 mole is 122 grams. The grams will cancel. And then we have 30.5 divided by 122. And I have 0.25 moles because moles are the only units left. Or you can use the equation from table T. So just to refresh your memory, the equation is the number of moles equals the mass given divided by the gram formula mass. So moles equals mass divided by the gram formula mass. So they want to know the number of moles. That would be your X. The grams given, 30.5. The formula mass, 122. And ta-da, it's the exact same mass. And so X equals 0.25 moles. Either way will work. All right, last example for doing mole conversions, and then we'll talk about hydrates. You have a sample of bromine, and notice that they're talking about the bromine gas, which is diatomic, so it's Br2. That contains 0.75 moles. How much does it weigh? So what they're looking for is an amount in grams. So that means we're going to need the formula mass. 2 bromines at, go to our periodic table. Bromines in group 17, it's the third one down, 79.9, so it's going to round to 80. 2 times 80 is 160 grams per mole. So again, you can either do it the factor label way, 0.75 moles times 160 grams per every 1 mole, and the moles will cancel. And we have 0.75 times 160 or 120, or we can use the equation. So it would be 0.75 moles equals the grams given, or what they're going to be looking for, and the gram formula mass is 160. So again, once you solve for x, we're going to multiply both sides by 160 so that cancels, and I still end up with 0.75 times 160, so x is still going to equal 120 grams. Put the unit there. Okay, so again, choose the method that you like best. It doesn't matter to me which one you use. The last topic for today's lecture are compounds that we call hydrates. And what happens in the hydrate is hydrate sounds like water, and that's exactly what we're talking about. When the crystals of an ionic compound form, sometimes water molecules get trapped inside of them. So when we did our separating a mixture lab, some of you ended up with masses that were greater than what you started with, and I said one of the things that sometimes happens when you're evaporating the water out of your salt is the water can get trapped inside of the crystals of the salt, in between the spaces. So when we have a hydrate, we show that water molecules are attached with this little dot. So when you see that little dot, you're supposed to think attached. It's not chemically combined. You can get rid of it just by heating it. Think of it as if you had, wet clothes and you threw them in the dryer. The heat from the dryer would get rid of the water, and your clothes weigh less once they're dry. Same thing happens with a hydrate. This compound is going to weigh more because it has this water stuck in the middle, and you can heat it over a flame or in a drying oven and get the water out, and then your compound is going to weigh less. This dot does not mean multiplication like it means in math class. It just means attached. So when we do the gram formula mass, this 5 is going to carry through to the water. So you have two choices for doing gram formula mass with hydrates. So the first way is to just count all of the pieces. So you have 1 copper and 1 sulfur and 4 oxygens plus the 5 oxygens from over here, so a total of 9 oxygens, and then 5 times 2, 10 hydrogens. So copper's formula mass is going to be, when we look over here, copper is next to zinc, 63.5, so we're going to round that to 64. Sulfur we haven't looked up yet. Sulfur right under oxygen is 32. Oxygen we have looked up at 16, and the hydrogen at 1. So 10 and 9 times 16 again, 144, and 1 at 32 and 1 at 64, and then we add all of these things together. So 64 plus 32 plus 144 plus 10, and that gives us a total formula mass of 25, or 250. Sorry about that. All right, I have a preferred way, and this is kind of a shortcut way. I add up just the ionic compound. So 1 copper and 1 sulfur and 4 oxygens. So that's 64 and 32 and 16, which 4 times 16 gives us 64 again. And then we add these together, so 8, 9, 10, carry the 1, 12, 15, 16, 160. And I have 5 waters. And water's gram formula mass is something that I have memorized. It's 18 grams per mole. So if I have 5 waters, I can just say 5 times 18, which gives me 90. And then to get my total formula mass, I just do the 160 plus the 90. And I'm right back to my 250. And you might say, why bother to do that? And it's not much of a shortcut. But one of the things that you might be asked to do is tell me the percent of water in the hydrate. If you do it this way, where you've multiplied it out, you already know out of the 250 grams, 90 of it is from water. So to do our percent then, we have 90 divided by 250 times 100, or 36%. So if you have to do the percent by math, doing the shortcut for the water makes it faster. So if we have, for example, a question like this: what is the percent by mass of water in the hydrate, sodium carbonate, decahydrate, deca for 10. This is called pent hydrate. This is decahydrate. The prefixes tell you how much. They're telling us the total formula mass is 286. So if I want to know the percent that's water, I can say, shortcut-wise, well, I have 10 waters at 18 grams apiece. That's 180 grams. So I can put the 180 out of the 286 and very quickly figure out what my percent of water is. 180 divided by 286 times 100 is going to give me 62.9% water by mass. All right, and one of the other things that they might ask you to do is say, well, if you have 3 moles of this stuff, how many moles of water do you have? Pretend these words aren't here and this is in an equation. That 3 is going to carry all the way through. So for every 1 mole of sodium carbonate, there are 10 moles of water. So if this carries through and I have 3 moles of sodium carbonate, I'm going to end up with a total of 30 moles of water. Last but not least is this lovely prefix, an. The prefix an or a or ab generally means not. So if I have something that is anhydrous, sometimes it also can refer to without. So it is not hydrated. It is without water. So if I have copper sulfate pentahydrate, that's my hydrate. If I have the anhydrous form of copper sulfate, that would just be the CuSO4 with no water attached. That would be its anhydrous form. So after you dry it out, it's now anhydrous. All right, that wraps up today's lesson.